Okay, so here's our scenario. You've got this on your notes here. You're working on a team at a chemical company that makes a yellow pigment for paint companies. Your team has been assigned the task of determining the percent yield for the procedure you use to make the yellow pigment. The procedure involves a precipitation reaction, which is also known as a double replacement reaction, in which you mix a solution of lead acetate and potassium iodide, both of which are soluble, and a bright yellow precipitate, lead iodide, will form, and that's the pigment that we're after. So the remaining compound, potassium acetate, remains dissolved in solution. We've already determined the balanced chemical equation. I don't know if you remember it or not, but here's lead acetate. Remember, Pb is lead, and then this is a polyatomic ion, and this polyatomic ion is called the acetate ion, and it has a -1 charge, and there are two of those, so my lead must have a 2+ charge, and then my iodide ion has a -1 charge, and my potassium has a +1 charge, so potassium iodide. And I've already said my iodine has a -1 charge. Whoops. And so I've managed to, so that should be Pb. And that'll have, again, a 2+ charge. And then my potassium, again, has a +1 charge. And my acetate has a 2- charge. And you'll notice that I have one acetate here, because that's what balances the potassium. But I've got two acetates over here, so I have to put a 2 in front of this to give me 2 potassium acetates. And I have to put a 2 here in front of the potassium iodide because I have 2 iodines over here and I have 2 potassiums over here. So for those of you that aren't familiar with balancing chemical equations at all, we'll get to that eventually here in the not too distant future. But for now, just try to understand the idea here that we can read this as saying 1 mole of lead acetate reacts with 2 moles of potassium iodide to form 1 mole of lead iodide and 2 moles of potassium acetate. So this means that the number of moles that I have to use of the potassium iodide has to be twice the number of moles of lead acetate. It doesn't really matter what number of moles I actually use. I just have to have a 2-to-1 ratio of this substance to this substance. And that's what this balanced chemical equation tells me. I have to have 2 times the number of moles of this as I do that. Now, that doesn't mean 2 times the number of grams. It means 2 times the number of moles, right? Because it's the number of particles that's important, not the number of grams. And then the other important thing here is that, Liana, can I get you to shut that door for me? So, the other important thing here is that for every 1 mole of this stuff that I use, I get 1 mole of this stuff. Okay? So the number of moles of my precipitate should equal the number of moles of my starting product there. So let's make sure you understand that the balanced chemical equation tells you this, right? Now, in your procedure, you're going to start with 0.1 molar lead acetate and 0.2 molar potassium iodide. Okay? You're going to start with 0.1 molar of this and 0.2 molar of this, and you're going to have 0.1 liters of both solutions. So you should be able to tell, since you have the same volume, that the amount of potassium iodide is twice the amount of the lead acetate. Okay? And I think we've already created a title and a purpose statement for this lab. You know that your first procedure statement addresses safety, and the second statement addresses the materials used. And I'm going to ask you to be thinking about the steps of your procedures as we go through this, okay? I've already made it so that we can actually complete the lab without having an actual procedure in front of you, okay? I'm giving you the basic parts of the procedure, and what I'm going to ask as you walk through the procedure, that you write down some notes here about how you're doing this, and we'll pull this all together when we get back to class after break. We'll sit down, we'll create the actual procedure together. I'm not going to ask you to do that over break by yourself. But this is going to be kind of an intermediate step between me showing you the procedure and you being able to do your own procedure. So the first thing that you need to be able to do is determine the mass of each reactant to make your solutions. You're going to start with your solutions here, right? But you need to know how many grams you need to measure out. How many grams do you use? Okay, and so we're going to create some procedural steps for that to happen. But in the meantime, scroll down to the end of, or the last page of this, and here's our data section. And the first thing the data section says is masses of reactants to make solutions. Here I'm showing you how you need to figure those out. Now we've already talked about this, but my experience is that chemistry students need lots and lots and lots of times to go through this in order to finally have it make sense to them. So our first goal, masses of reactants to make solutions. How many grams? How many grams? So when you're at your tables, your first step is going to be, I need to figure out how many grams I'm going to use. I've given you the molar mass of the lead acetate. I've given you the molar mass of the potassium iodide. And I've given you the formulas that you need to figure this out. I want to know how many grams of lead acetate I need to make my solution. You remember, anytime you have grams, your brain should know by now, anytime I need grams, I only have one formula that can find this out for me. Grams equals moles times molar mass. I shouldn't have to think about this anymore. Grams equals moles times molar mass. And then your brain should say, I don't have moles. But then you should remember that because you know that molarity equals moles over liters, that the way that you're going to find molarity, or number of moles, is to multiply molarity times liters, right? So I've given you the molarity, right? And I've also given you the number of liters. For the lead acetate, the molarity is going to be 0.1 molar. For the liters, it's going to be 0.1 liters. So I need to multiply those two things together, and then I'm going to plug that answer into there, and I'm going to plug that answer into there, and that's going to tell you exactly how many grams you need to make that first solution. Then you're going to do the same thing with the potassium iodide. Potassium iodide, how many grams do I want? Well, I need to figure out the number of moles first, molarity times liters. I've given you those things, 0.1 or 0.2 molar for that, 0.1 for that. You calculate that, and then you do that, And you know that? Okay, so that's going to give you the total number of grams. Okay, so ultimately we're going to create a procedural set of steps to remind us how to do that. If we go back up here, then those steps, and we'll write it out in words how we calculated that, right? Okay, so that's what that space is for. I would encourage you to write down some notes during the time that you're doing this to remind you how to accomplish this. Okay? Now, preparing the lead acetate solution, this first solution, the lead acetate solution right here, how do I make it? Okay? You will use the volumetric flask for that. Remember, all you do for that, and I've given you some lines here to take some notes on this. Again, we walked through it and we practiced it a little bit. You will use the volumetric flask, and for the volumetric flask, you'll put the solute in the flask, and then you'll fill it part way, right? Remember that? Because we need to have room to swirl it around in. We'll fill it part way, and then you'll dissolve it, and then there's this little mark up here. You'll fill it most of the rest of the way, and then you'll use the disposable pipette to fill it the rest of the way, right? And we need to have the measurement at the meniscus, okay? So I don't want to see people looking down from up above to try and make sure that their meniscus is at the level of that, because that won't work. You have to have it at your eye level, right? Okay, so that's for the potassium, or the lead acetate solution. And again, take some notes on how you do this and remind yourself so that we can create a real procedure when we get back from break. Potassium iodide, you're going to use the graduated pipette and a pipette bulb and an Erlenmeyer flask. And remember, an Erlenmeyer flask is this kind of conical shaped thing, right? And it has some measurements on the side. Oh, by the way, a note that you should make for this: when you make this, we're using tap water, and tap water has chloride ions in it. Okay? Tap water has chloride ions in it, and the lead in there will actually bind to the lead in here will actually bind to this, to the chloride, and it will turn the solution kind of a white color. So your solution will end up being a cloudy white. Okay, this does not remove enough lead to change our results any. Okay, this does not remove enough lead to change our results any. So just be aware that you're going to get that cloudy white appearance and not to worry about it. With the Erlenmeyer flask with the potassium iodide, you'll put this in here, and then you'll use the graduated pipette and the bulb, right, to deliver 100 milliliters. Now, this has 25 milliliters, so you'll need to do it 4 times, but we just want to get some experience in using the pipette, the bulb, so everyone should try to do this if possible. And then you'll deliver 100 milliliters, but you'll find out that the amount of water that you put in here is probably going to be greater than the 100 milliliter mark on the Erlenmeyer flask. That's because Erlenmeyer flasks are terribly inaccurate, and don't worry if you're 100 milliliters from this is a little bit more than what there's a 100 milliliter mark on the Erlenmeyer flask shows. Okay, and then you'll just dissolve this by swirling the flask. And so then you'll have two solutions. You'll have one in the volumetric flask. You'll have one in the Erlenmeyer flask. Okay, then you're going to create and determine the mass of the precipitate. So you're going to dump the two things together. So you're going to add the volumetric flask solution to the Erlenmeyer flask solution, not the other way around, and you'll get a precipitate. Okay, and this yellow precipitate is what we want. Okay, now we're going to filter this using a funnel and another Erlenmeyer flask, and the filter, or the funnel will have filter paper in it. Okay, and I'll give you the filter paper. I haven't put it out yet, but I'll give you the filter paper, and that will collect all of the precipitate. Now, initially, it will be very moist because it's still got liquid in it. Okay, it's still got liquid in it, and we don't want to weigh the liquid. We want to weigh or mass the precipitate. Okay, so I said here, make sure you find the mass of the filter paper before you collect the precipitate. So you're going to take your piece of filter paper and you're going to take its mass and you're going to put that in the data table, mass of unused filter paper. Okay? And then you're going to take the filter paper with the wet precipitate and put it in our drying oven. Okay, you're going to put it in our drying oven, and it's going to dry for a few minutes, and it shouldn't take real long. It's going to dry for a few minutes, and then you're going to take the dried precipitate and mass it again. Okay, and that will give you the mass of the filter paper plus the precipitate. And if you subtract this from that, you'll get the mass of the precipitate. Okay? Now, how are we going to figure out the percent yield? Okay, we remember that the number of moles of lead acetate that I start with should also be the number of moles of lead iodide that I get. Okay? The number of moles of lead acetate should also be the number of moles of lead iodide that I get. So, what you're going to have to do is, given the number of moles of lead acetate that you figure out, you're going to find that you have a number of moles of that. That will also be the number of moles of lead iodide. And I'm going to go down here and write. Okay, this will also be moles of lead iodide. That should be the number of moles that you get. Okay? You're not going to get that much lead iodide. There's going to be some mistakes that are made along the way and little inaccuracies in the way we do things. Okay? So you're not going to get this number of moles. You're going to get less moles of lead iodide than you do of this because our process is inefficient. That's why we're doing this in the first place. We want to figure out what the percent yield is. Okay? So what you're going to do is you're going to, since you know, oops, this will be the number of moles of lead iodide. Since you know how many moles of lead iodide you're supposed to get based on this calculation, I'm supposed to get this many moles of lead iodide. That will allow you to figure out how many grams of lead iodide. Okay, if I know how many moles of lead iodide, right, grams is going to equal moles times molar mass. So you can figure out the number of grams of lead iodide, and you can divide that by the number, or you can divide the number of grams of lead iodide that you get by the number of grams of lead iodide that you're supposed to get. And that will be, and you multiply that times 100, and that will be your percent yield. So percent yield is going to be grams of lead iodide you actually get divided by grams of lead iodide you are supposed to get, and multiply that times 100, and that will be your percent yield. Okay, so this is the procedure. Okay, again, as you're doing this, write notes. You've got the basic outline of the procedure, but write notes about how you're doing it so that we can come to class next time and create an actual full-on procedure and maybe write up a conclusion at the same time as well. Okay? So that's how we're going to accomplish this. Yeah. Yeah. Sorry.